There are many different types of shell and tube heat exchangers, and each one is designed to accomplish a specific function in a process. Condensers are one type of shell and tube heat exchanger. They're designed to convert gases or vapors into their liquid states. Here's an example of a typical condenser. It's used to turn steam into water so that the water can be reused in a steam generating system. Condensers can also be used to cool and condense product vapors. For example, the vapor produced in this distillation column flows into a condenser and is converted to a liquid. Depending on the process involved, the liquid formed in a condenser may be referred to by different names. The water that's formed when steam is condensed is called condensate. On the other hand, the liquid that's formed when product or byproduct vapors are condensed is often called distillate. To get a better understanding of how a condenser operates, let's look at an illustration of a condenser that uses cooling water to condense product vapors into distillate. This condenser has a shell, tubes, tube sheets, a vapor inlet, a cooling water inlet called a head, a distillate outlet, a cooling water outlet head, and a receiver. On this type of condenser, the cooling water heads may also be referred to as water boxes. During operation, on the tube side of the condenser, cooling water enters through the inlet head, passes through the tubes, and flows out of the condenser through the outlet head. On the shell side of the condenser, vapor passes through the inlet and flows around the tubes. When the vapor comes into contact with the cool surfaces of the tubes, heat is transferred from the vapor through the walls of the tubes to the cooling water. As heat is transferred to the cooling water, the vapor cools and condenses on the surfaces of the tubes. The condensed vapor, or distillate, drips off the tubes and falls to the bottom of the shell. It then flows through the distillate outlet and into the receiver. The receiver receives or collects the distillate that drains from the shell of the condenser. The distillate is usually sent on for further processing or to storage. Now, as the vapor condenses, a low pressure is created inside the condenser. This low pressure draws more vapor into the condenser. In order for vapor to continue to flow into the condenser, the pressure inside the condenser must be lower than the pressure of the vapor entering it. Condensers can be operated at almost any pressure, as long as it's below that of the entering vapor. For example, the vapor entering this condenser is at 250 psi, and the condenser is operating at a pressure slightly less than that. On the other hand, this condenser is operating under a vacuum, because the vapor entering it is near atmospheric pressure. In a condenser that operates under a vacuum, the condensing vapor normally maintains the vacuum. However, when the condenser is started up, auxiliary equipment, such as a steam jet air ejector, may be needed to establish the initial vacuum. A steam jet air ejector consists of a steam inlet, a nozzle, a suction port, and a combining tube. Normally, the combining tube is connected directly to a small condenser called an air ejector condenser. As the steam passes through the nozzle, it is accelerated. As the fast-moving steam leaves the nozzle, it draws air in from the main condenser through the suction port and to the combining tube, where the air mixes with the steam. This mixing process is referred to as entraining. As the steam and air mixture flows out of the air ejector, an area of low pressure forms in the air ejector suction port. This low pressure draws additional air in from the main condenser. This air also becomes entrained in the steam, and the process continues. The final result is that the pressure in the main condenser decreases. In some systems, the air ejector and its condenser are shut down after a vacuum has been established in the main condenser. But in some processes, the air ejectors remain in service to remove air and other gases that won't condense. You see, non-condensable gases can build up inside a condenser. When this happens, the gases insulate or blanket the tubes and reduce the amount of heat transferred in the condenser. As a result, less vapor will condense, and the pressure inside the condenser will increase. The increase in pressure may reduce the flow of vapor, or it could stop the flow altogether. As an operator, you may be responsible for the operation of many different types of heat exchangers, including condensers. So it's important for you to understand how they can be started up and shut down. To get an idea of the steps involved in starting up and shutting down a condenser, we'll watch an operator as he places a condenser in service and then takes it offline. The condenser we'll use in our example is part of a distillation process. It operates at a pressure well above atmospheric, and the cooling in the condenser is accomplished by water that passes through the tubes. Before starting up this condenser, the operator verifies that the valves on the condenser and its associated equipment are properly lined up according to his startup procedure. With the valve checks completed, the operator opens the vent valve on the tube side of the condenser. Then he partially opens the cooling water inlet valve. The sound of escaping air means that cooling water is filling the tube side of the condenser. When the tube side is filled, a stream of water flows from the vent. Then the operator closes the tube side vent valve. With the vent valve shut, the operator fully opens the cooling water inlet valve. The cooling water flow is controlled by the outlet valve, so the operator partially opens the cooling water outlet valve to a predetermined position to establish flow through the condenser. At this point, the control room is contacted and the process can be started. When the distillate reaches a predetermined level in the receiver, the distillate pump is started, and the condenser startup is complete. Now, for a condenser that operates under a vacuum, the air ejectors would be started before the process fluid flow is started. This would remove the non-condensable gases from the condenser and create the initial vacuum. In addition to starting up a condenser, operators are also involved in taking condensers out of service. During a condenser shutdown, if the flow of cooling fluid is stopped before the process fluid flow, the condenser could overheat and be damaged. Once the process has been shut down, the condenser can be shut down for maintenance. The operator shuts down the condenser by closing the cooling water inlet valve and closing the cooling water outlet valve. Since the condenser is being shut down for maintenance, the tube side will need to be drained. That's done by opening the tube side vent valve and the tube side drain valve. Once the tube side is drained, the shutdown is complete. In some cases, it may be necessary to purge a condenser with an inert gas after shutdown. Purging removes vapors that could promote a fire when exposed to air. When a condenser is up and running, operators regularly monitor its performance. Keeping a close watch on condenser operation can help ensure that the condenser is working properly. Let's take a look at some of the routine checks that operators typically make in order to identify problems and ensure that a condenser operates safely and efficiently. One important check is the level in the receiver. This can be checked using a sight glass on the receiver or from a display or a chart recorder in the control room. If the receiver level is too high, the condenser shell could flood, reducing the condenser's efficiency. If the level in the receiver gets too low, equipment located downstream of the condenser could be damaged. For example, if the receiver level gets too low, the pump that's used to pump distillate out could cavitate. The cavitation could prevent the pump from operating properly and damage the pump. A controller on the receiver automatically maintains level. An abnormal level could be an indication of a problem with the controller. A low level could also be an indication of a problem with the cooling water flowing through the condenser. Another important operator check is the unit's temperatures and pressures. These indications can be checked on instruments attached to the condenser or on displays in the control room. One pressure reading that is important to check is the receiver's pressure. If the pressure in the receiver drops too low, the product liquid may flash back into a vapor. The condenser's pressure is also important to check. On condensers that operate under a vacuum, insufficient vacuum may affect the efficiency of the condenser. Too little vacuum can result from steam pressure being too low at the air ejectors, from air leaking into the condenser, from too little cooling water flow, or from the cooling water temperature being too high. Many condensers have control valves that regulate the unit's cooling water flow. An abnormal cooling water temperature could be an indication of a problem with the control system or with the cooling water system. Contamination in a condenser may be caused by a tube leak in the condenser. One way to check for contamination is to take a sample of the lower pressure fluid and test it for the presence of the higher pressure fluid. In some cases, contamination in the sample can be seen. In addition to sample test results, conductivity and pH readings of cooling water may indicate a tube leak. If there is any indication of contamination, it's important to determine the source of the problem and take the appropriate corrective action. In this part of the program, we looked at how condensers operate, and we examined some typical condenser startup and shutdown procedures. We also covered some of the basic checks that operators typically make on condensers. Now let's try some practice questions on this material. On the shell side of the condenser, vapor passes through the inlet and flows around the tubes. When the vapor comes into contact with the cool surfaces of the tubes, heat is transferred from the vapor through the walls of the tubes to the cooling water. As heat is transferred to the cooling water, the vapor cools and condenses on the surfaces of the tubes. The condensed vapor, or distillate, drips off the tubes and falls to the bottom of the shell. It then flows through the distillate outlet and into the receiver. When the tube side is filled, a stream of water flows from the vent. Then the operator closes the tube side vent valve. Contamination in a condenser may be caused by a tube leak in the condenser. One way to check for contamination is to take a sample of the lower pressure fluid and test it for the presence of the higher pressure fluid. In some cases, contamination in the sample can be seen. In addition to sample test results, conductivity and pH readings of cooling water may indicate a tube leak. If there is any indication of contamination, it's important to determine the source of the problem and take the appropriate corrective action. Kettle-type reboilers are a type of shell and tube heat exchanger. They're primarily used to vaporize process liquids from a distillation column and return only the vapor back to the column. Let's look at an illustration of this type of reboiler to see how it works. The major parts of this reboiler include a shell, a tube bundle, a tube inlet, a tube outlet, a shell inlet, baffles, a vapor outlet, an overflow weir, and a liquid outlet. In this reboiler, steam is used to heat the process liquid. When the steam passes through the tubes, it transfers some of its heat to the process liquid. As the steam transfers its heat, it condenses into water, which is returned to a steam generating system. The process liquid from the distillation column enters the reboiler here. The liquid flows around the baffles and tubes and receives heat from the steam. The overflow weir acts as a dam to ensure that the tubes in the reboiler always stay covered with the process liquid. As the process liquid is heated, some of the liquid boils off as a vapor. The vapor separates from the liquid and collects in the dome-shaped space above the tubes in the shell, and then flows back to the distillation column. The process liquid that does not boil off is pumped from the reboiler and sent to where it can undergo additional processing or be stored. A shell and tube heat exchanger known as a Thermosiphon Reboiler is used to heat process liquid from a distillation column to produce a vapor. Then the vapor and the process liquid flow back to the column. Let's look at an illustration of this type of reboiler to see how it works. The major components of this reboiler include a shell, a tube bundle, a tube side inlet, a tube side outlet, a shell side inlet, and a shell side outlet. In this reboiler, oil that's heated in a furnace is used to heat the process liquid. The hot oil passes through the tubes and is then returned to the furnace where it is reheated. The process liquid from the distillation column enters the reboiler shell and passes around the tubes. Heat from the hot oil vaporizes part of the process liquid. The mixture of liquid and vapor is then returned to the distillation column. The flow of the process liquid and vapor is caused by the difference between the density of the liquid entering the reboiler and the density of the heated mixture that's returning to the distillation column. The heated mixture in the reboiler is less dense than the liquid coming in from the column. This difference in density causes the heated mixture to rise out of the reboiler and return to the column. The result is a natural circulation between the reboiler and the distillation column.